Welcome in the video lecture series of operating system. Myself Avadhesh Dixit, Assistant Professor IT, Dr. Ramanol IET Ayodhya. Now today we are going to discuss a very important algorithm of deadlock avoidance known as the banker's algorithm. As we already know that deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that the circular weight conditions never exist. The resource allocation state is defined by the number of available and allocated resources and maximum demand of the process. Deadlock avoidance, as we have already taught in our previous lecture, that if a resource have a single instance, then we should use resource allocation graph for deadlock avoidance problem. That means we just ensure that there should not be any circular cycle in the graph RAG, resource allocation graph. Now in deadlock avoidance, basically we have a two main concept. In a first concept, we just test the system, either the existing system is in safe state or not. If there are many processes in the system, then we just examine that either there has any safe sequence in the system or not. If there is a safe sequence of processes found, then we go ahead and execute. If there is no safe sequence found, then the system will not allow to execute the processes because there may have a deadlock. So, and second thing in deadlock avoidance algorithm, if any request of process comes, assume that presently the system is in a safe state, and if any request comes, then we have to examine that either that request will lead the system in safe state or not. If the new request arrival, the system becomes unsafe, then the kernel will not allow the process to execute. Then there are basically two concepts in the deadlock avoidance, and these concepts are implemented by the banker's algorithms. Look here, the banker's algorithm. Banker's algorithm, as here refers, the most important concept of the banking, that means a bank never allocate their cash to a particular person or excessive cash withdraws. He always keep balances of their cash in their system. That means no any request, small or medium request, can be discarded by insufficient of the cash. And similarly here in banking algorithm, banker's algorithm, there are basically two parts. First is a safety algorithm and second is a resource request algorithm. So now here we are going to discuss the safety algorithm today. Now look here, the data structure what used in the safety algorithms. First is a available. So now here available, this is single dimension array, or you can say single dimension vector. It denote the available number of instances of different resources. Like how here in this example, there are three resources A, B, and C, and three instances of A, four instances of B, and four instances of C are available in the system. Now, second data structure is a max. This max shows the maximum demand of the resource related to a particular process in the system. And it is also two-dimensional array of n cross m. If we represent the number of processes by n and number of resources by m, that means it is represented by the two-dimensional array or two-dimensional matrix n of n cross n. So look here, maximum demand. Here A, B, C, they are resources, and for every process there are maximum demand. For process P1, maximum demand of ABC is 368. For process P2, maximum demand of ABC is 433, and for P3 is 344. Now allocation. Here allocation is also a two-dimensional array or two-dimensional matrix, which here represent the number of instances of resources allocated to a particular process. It is also two-dimensional, and here look here, process P1 have a 2, 2 and 3 instances of resource ABC. Similarly, process P2 and P3. And now look here, work and finish. These are the temporary variables used in the algorithm, and these two variables just represent a single dimension array. Here work just used to store available number of resources at particular point of time, and finish data structure is used just to ensure that all the processes have tested or treated, they are tested for that they are eligible for execute or eligible for wait. Then finish variable is used. Now look here, the safety algorithm. In safety algorithm, in first step, we initialize the work variable by the available number of instances, and another is a finish I. Initial value of the finish I will be false for all I 1, 2, 3 and n. Here are three processes, then there is only 3, 1, 2 and 3. Now step 2, find an I such that finish I is equal to false and need I less than equal to work. And first of all, here finish let I is equal to 1, finish 1 is equal to false, and need I less than equal to work. If need I less than equal to work, then we here jump to the step 3. Otherwise, we jump to the step 4. If no such I exists, and go to the step 4. In step 3, we again calculate the value of work plus allocation, and look here, if need I less than work, then that process will be allowed to execute by the kernel. And after executing, their allocated resources will be released. These allocated resources will be released. Then that allocated resources will be added into the work variable. That means the total number of work or allocated resources will be updated. Now, if no such I exists, then it transfer to the fourth and it check whether finish I is equal to true. For all I, then the system is in the safe state. That means it ensures that if all the processor has tested or not. If they are not tested, then to jump to test the process which are not treated here, are not tested here, and if they are made any safe sequence of the processes, then we say that our system is in safe state and that will allow for execution. If that is not, that means system is an unsafe state and not allowed for the execution by the kernel. This is the main concept of the safety algorithms. Now, here we have an example and we will test all the processes. We will test all the processes. Look here we need not finished and work variable, because these variable will be needed when we will make the program in a software. Right now here one by one we will treat the process. Now look here, for I is equal to 1 we take process P1. Now right now look here, we require the need variable need. It is also two-dimensional array and need is equal to maximum demand minus allocations. So first of all we will find out the need matrix here. Look here, need matrix, need. In need matrix, look here, here is a process A, B, C resources. Now process P1, process P2 and process P3. Look here, in process P1, 3 minus 2 is equal to 1, 6 minus 2 is equal to 4 and 8 minus 3 is equal to 5. Again here 4 minus 2 is equal to 2, 3 minus 0 is equal to 3 and 3 minus 3 is equal to 0. Again 3 minus 1 is equal to 2, 4 minus 2 is equal to 2 and 4 minus 4 is equal to 0. So this is the need matrix. Now first of all we calculate the need I, means need 1. Need 1 is equal to what? 1, 4, 5. 1, 4, 5. And we test if need is less than available. Means here need is a 1, 4, 5 and available is a 3, 4, 4. 3, 4, 4. Look here, 5 is greater than 4, that means the condition is false. This condition is false. Here need is less than available is a false. It means P1 have to wait. Then P1 will not be allowed to execute for execution. That means P1 need to wait. P1 need to wait. Now again take process P2. P2. Find out need 2. Need 2 is equal to what? 230. 230. And again check need 2 is less than available. Means 230 is less than 344 and this is true. This is true. That means 230 is less than 344 because 2 is less than 3, 3 is less than 4 and 0 is less than 4. That means this condition true. That means the process P2 will be in the safe sequence and means process P2 will be allowed to execute. Now Again, here when process will execute, their allocated resources will be released. Then allocated resources will be released. That means total availability of resources is equal to available is equal to available plus allocated. Look here. Earlier available are 344 and allocated in process P2 is 203. 203. That means this is equal to 324, 404 and 437. That means now newly available are for 547. Right now, similarly we will check process P3. Process P3. Now, for P3, need 3 is equal to 220. 220. Then need 3 220 is less than available 547. This is true. Here it means process P3 will be allowed for execution for kernel. Execution for kernel. And after execution of the process P3, there will be resources released 1 to 4. That means available number of resources will be will be equal to the current availability 547 plus here release resources 1 to 4. 1 to 4 and this is equal to 516, 426 and 7 and 4 11. 547 plus 124. 124 here allocated in process P3. That means right now 6, 6, 11s are available. Now again we will test that if any other process are waiting or not. Now look here, process P1 is still waiting. Then we calculate the process P1. For process P1, need 1. Here need 1 what? 145. 145 is now less than available means 6, 6, 11. 6, 6, 11. Then P1 will be this is a true. Then P1 will be allowed to execute and after executing the resources of allocation resources will be released. That means last available is equal to total available means 6, 6, 11 plus 2, 2, 3. 2, 2, 3 that is equal to 8, 8 and 14. Right now all the processes have executed, have tested and the safe sequence is here. Safe sequence is equal to P2, P3 and P1. Here it means safety algorithm tests that there has a safe sequence. First will execute P2, then P3, then P1, then there will be no any possibility of the deadlock into the system. So this is all about safety algorithm. Thank you for watching the video.